Well, thank you, everybody. My name is Mark Ehlen. I've been looking at this piece of software now for about 20 years, so I wanted to give you a little bit of a background on what Life-365 is and go back to an original late 90s meeting at NIST with Jeff Fronsdorf, where they called, we need to talk more about not just strength, but also durability of concrete. And kicked off a whole process that resulted in this committee, the subcommittee A on service life, to develop an approach for estimating the service life of concrete subject to chloride-induced corrosion. So my involvement early on was, well, the technique itself was developed by this subcommittee, signed off, published, reviewed, and then software was written by Evan Bentz and the late Michael Thomas. They both developed the first draft of this technique before it went through review. A phenomenal technique at the time, because at the time it was just a gleam in people's eyes, and the idea of coming up with a consensus model that would be freely available and subject to review and discussion was new, at least to concrete service life. And so then a piece of software was written, and then I was brought on as an economist to add life cycle costing, because the first review was, yeah, that's great about service life prediction, but what does it cost? What are the benefits from a cost standpoint? I'm not going to talk about the cost at all today, but through the course of being involved in the cost, I've become heavily involved as the prime hands touching this software, maintaining it, fixing it, developing a new user interface, but I want to give most of the credit to Michael Thomas, the late Michael Thomas, and Evan Bentz, who's not here. Fantastic technique for using laboratory results to develop first estimates of concrete initiation to corrosion and propagation, and then some follow-on techniques for uncertainty. And so what we have here as a piece of software is its only chloride transport model. It does not do cracking. It does not do other types of attack at all. It's just chloride. It does come with some presets that now are a little long in the tooth. Some of them are still really good, like silica fume, fly ash, and one other. But it's missing some others. But what they did in the process of this model was always allow you to override some key parameters, so that if you have a new admixture like this HP, the long name is the one that Neil mentioned. You can use those. You can use any number of those. You can use new lab results. And I'll go through the lab results that are required to use this as is, but it's open to these other techniques. And so I did the best I could as an economist and longtime user of Life-365 to apply those given set of conditions and then come up with estimates. But the story is a little bit longer than that, and I'll get to that part of it. I still consider a comparative analysis tool. If you've got a structure, like a slab, and you've got multiple potential concretes you could use, which one is better than the other, with fairly good estimates of what initiation and propagation are. It doesn't mean that you're going to hit that number in 157 years, you're going to start to see rust, but it's a good lab-based estimate of what the corrosion is likely to be over the course of that structure. Open specification that I mentioned, the technical manual itself is extremely transparent. It talks about all the lab tests. It talks about the chloride mechanism that's modeled in 2D and one-dimensional finite differencing, and is documented as much as possible. If somebody wanted to write another piece of software that does the Life-365 approach, there's enough information in there for you to be able to do that. It's a lot of work, trust me, but you could. Today I'm going to talk about the service life estimates for those three mixtures. It looks like there's other options that could have been used if you're trying to game the concrete and come up with the longest lasting for each. There are additional things like you mentioned about the enhanced. There are other additions you could make to the concrete itself so that it would last longer. I just took the three as is to give you a demonstration of what first estimates are, and then we can talk about sensitivity analysis and probability analysis. Okay, those three uncertainty estimates. How did we get to where we are? I covered most of this, but this gives you a quick timeline. It's really because of Michael and Evan that we have this implementation, and we've pretty much preserved what that is. I came in to add life cycle costs, heavy software verification. There's an Easter egg in the model where you press a button and you can see a full model validation of that version against the original version of Life-365 to make sure that the estimates as computed now match the original estimates. And then the manual itself only gets larger in terms of more detail, just to keep it transparent. Also, back in the day of Tony Kajundek, we added in the ASTM-C 1556, so you can put in numbers from lab tests and come up with the maximum surface concentration and the apparent diffusion coefficient, which we do use in one of the estimates here. And then this is a list of the concrete diffusion lab tests that were used to make this model. They may be different than the tests that you use now. In the manual states clearly that NT build 443 was used before there was a C1556, but now that there's a C1556, we would use that instead. But for the sake of posterity and the way the model is used now. The manual is full of graphs of dots of different mixes and lines through them, straight or curved lines to show you, one, what the relationship is, and two, the range of test values that create uncertainty, if you will, in those basic relationships. But the model uses basic relationships. The model itself is pretty old now at this point, so it's widely used, published, and compared. You can go to Google Scholar and see probably 100 articles comparing it to other models, using it on real bridges in Singapore or other places. There's lots of heavy use of the model. And right now we're working hard to complete a web version of this. I'm debugging it with my thumb. It works on a phone, tablets, desktop computers. If you have the desktop version of the model, you can create a project file there, upload it to the web, and run it on your phone. Finish that file, download it, and put it back on your desktop. So it's transparent in terms of the data file format. So that's what Life-365 is. Again, on the documentation, if you're really interested in this, I don't know if you can get CEU credits for this, but it's very specific about how it calculates two-dimensional finite differencing and one-dimensional with the mathematics behind it. Needed the math to do the software verification processes that are in the model now, document what it is, and then do spot calculations to make sure that it's calculated correctly. That kind of thing. How to use, and then also how not to use. If chloride is not your prime transport mechanism, this is not the model for you. And then finally, this is the Easter egg in the model itself. It goes through hundreds of tests for 1D, 2D, square and round columns, different membrane sealers, basically a parametric analysis to see at the very right-hand side, it compares in percent terms the difference in the initiation period of the original Evan Bentz model in C, in the language C, and this version, which is in Java. And the numbers are fairly tight, given numerical precision that's different in platforms and a host of other things. But the important thing is it's all documented. Basic and advanced modes in this model. This model is used by a lot of engineers just to see what the relative value of a new admixture would be, just the relative value. And so it comes with a number of presets, water cement ratio, class F fly ash, slag, silica fume, different rebar types, inhibitors, corrosion inhibitors, barriers. Those are all presets. You choose those, and it adjusts either the concentration to initiate corrosion or the hydration parameters like M, those kinds of things. But the real superpower of this is this custom, where you can put in your own D28, your own M factor, your own hydration period, your maximum corrosion, your corrosion to your CT, sorry, the corrosion level to initiate corrosion, propagation years. For the last example, for the HP40, this was essential because that one had laboratory data as published by an ACI document that showed what those parameters could be adjusted to represent what this HP mix does. So I'll get to some of that here in a second. And then lots of screens to slice and dice this kind of data. It's, in many ways, for me, it was an instructional tool. It taught me sort of the difference between these different factors. It's fast, so you can use it for sensitivity analysis. If you're not sure on D28, then you can modify plus or minus 10% and see what effect it has. If you're not sure about M, you can modify plus or minus 10% and see what the effects are on outcomes. But the goal is to find out which factors really matter for determining service life and then focus on those. And the probability charts will give you some insight as to what that is, because based on these different mixes, Life-365, using Evan Bentz's technique for uncertainty, shows big differences in asymmetric variances. The third, I think it's kurtosis, is the third. First is the average, second is the variance, and the third is kurtosis, how asymmetric they are. Okay, so to give you an idea of how I use this data for Life-365, I had to convert all of these part per million numbers into percentages because Life-365 does percent weight of concrete. So it's a straightforward calculation, but I have to take these. You can see in the silica fume line, we're replacing some of the cement with silica fume, and in the HP, I'll just call it HP, the HP line, we're substituting the HP for some of the cement. But basically coming up with percent amounts of admixtures that are percent of the cement, not of the overall concrete, but just the cement. The other details are things that Life-365 anyway just takes as an average kind of mix. It does not try to model chloride movement through different coarse and fine aggregate mixtures, the kind of detailed modeling that's happening now. It comes up with a number based on some laboratory results, and not the actual mechanical modeling of the chloride movements. Water-cement ratio, it does take. Design error, no. On the right-hand side for elements, it's got two basic types. One is a flat slab, which really represents chloride on one side. Like if this was the slab, you have chlorides on top, no chlorides on the bottom, and you're capturing the gradient of chlorides from the concentrated level to a zero, essentially a zero level. A marine pile is round, where you're exposing it to, round or square, you're exposing it to all the external sides, taking the worst location for the amount of splash. And then for a marine wall, in the past we've modeled that as a slab that's tilted up. That makes sense as long as you just got splash on one side and not on the other. If you got splash on both sides, you really have to go to something that's more like a marine pile because you're getting hit from a number of sides. And you want to be able to make an expert judgment, if you will, about what is the maximal, what's the most realistic level of chloride exposure and intrusion based on your structural type. Exposure conditions for de-icing salt, submerged, and splash. Life-365 has some presets, roughly speaking, for what those are, but I've already had to override some of the exposure conditions, and so I don't want to go into trying to choose those presets. I want to go into something that looks closer to the actual numbers. And some of those numbers, like the maximum surface concentration, I can convert those into percent weight of concrete and use those numbers. The cover is pretty straightforward. Life-365, I think, will go down to 2 inches. Below that, we start having a problem with numerical accuracy of the model because it's a slicing model. Finite differencing is like finite element, where for a slab like this, it'll cut it into a bunch of layers, and each layer is considered homogeneous, and you're then doing the differences between those homogeneous layers. You get to too few layers, and your accuracy goes way down. It goes way, way down. It becomes very, very sensitive to your depth. So we're good here in terms of that cover depth. I used the black bar initiation period and converted that into percent weight of concrete. The default value was 0.05% in the model. So this is essentially 50% higher, like the steel is better than it was 20 years ago. You all can speak better to whether it is better than it was 20 years ago. But that's what we used. Could have upped it to something to the next number, the 2500. Maybe that's in Life-365, you've got epoxy coated, you've got stainless steel in there. Those are presets. But you could also override and put in your own value if you want to. Hydration time, it has a default of 20 years, but you can override that as well, right? 25, you're right, thank you. It's 0.2 for M, but it's 25 years. Okay, so lots of details here, right? The chance that you're going to get 100% on this test is almost zero. And that's okay, because it's really, really hard to match exactly not only what you designed the concrete to be, but what comes out of the ready-mix plant and then what it looks like 100 years from now. The chances of getting an A+ on that are low, and that's okay. Okay, on the structure type, this gives you some images from Life-365 to show for a concrete slab. The green is higher concentration, the blue is no concentration. That's the propagation mechanism for the concrete column. It's around the perimeter. It could be a square column too. And then concrete column is just the marine wall, in our case, is a tilted concrete slab, but higher levels of concentration because it's getting splashed quite a bit. Provided structural dimension size matters, where One of the weaknesses of Life-365, and you get lots of technical support questions on this, is use an 8-inch slab with a 2.5-inch cover. You get a service, you come up with a service life, let's say 25 years. You go back to it and you change the depth of the slab to 16 inches, still with a 2.5-inch cover. And you're going to come up with an answer of like 30 years. And so then the call is like, well, I didn't change the depth of the cover. Why am I getting a different service life for a different depth of slab? And it's because as modeled, it's modeling a concentration high, a gradient down to no concentration at the bottom. So the deeper you make the slab, the longer the gradient and the more time it's taking to pull. It's just a different pull than if it's 8 inches or 4 inches. It's just a different pull. So you will get slightly different answers. It shows how the model isn't necessarily perfect representation of reality, but that's okay. I've got a blanket statement to say about that later. Monthly temperatures, it turns out that Life-365 has built in the temperatures that were given. So I just use those as a drop down. But we have different maximum exposures, and so the data that comes with it is TRB data, I think, or I think it's TRB data. It has to do with not only maximum concentration on Boston roads, but the time it takes to get up to those. So it says 7.1 years to get up to the maximum concentration. So that makes sense for a bridge deck, maybe in the wintertime where cars are coming in and they're bringing road salts to it, that kind of thing. But it doesn't make sense for a seawall. You're going to be getting maximum concentration right away, every day. As soon as that thing's up, you're going to be getting maximum. So the time to get to maximum is different across these different types. So that's where I'm saying buildup is immediate, whereas the de-icing salt buildup is over time. Study period, 250 years sounds crazy, but you need the model to give enough graph space so that it can show for you can see the uncertainty of this estimate. There will be a best estimate, but the uncertainty can be fairly wide. And then life cycle costing, I say nope. By the time you got out to 250 years, this building won't be here. Our great-great-great-grandkids won't be here. We'll be living on Mars. There's a totally different set of conditions. So while the concrete may last 250 years, the study period at some point doesn't make a lot of sense. So you just have to be careful when you're reporting that this bridge will last 250 years. There are other forces at bay. And then the overall analysis strategy is this tool is very fast for a first estimate. It gives you time to be able to try alternates for the inputs to find out what really matters. If you're not sure about temperature or maximum concentrations, you can modify those and very quickly it'll give you new estimates. And then you can plot sort of curves, if you will, based on different values. If you're really after confidence in your answer, you really need to do sensitivity analysis. And then the uncertainty analysis, as written, is useful, but the ranges are very wide, and I'll show that. Okay. So for these three, the cement type, Life-365 doesn't really give you a choice to change it. It's not one of the options, so I ended up using what was in there, as opposed to trying to replicate some of the performance that comes out of these alternate mixes. Mixed design proportions, I used Life-365 defaults. The binder chemical compositions, did not use those as well. Use the defaults. I did use the water-cement ratio. And then for the HP40, I needed to use the laboratory results from C1556 because I needed an apparent diffusion coefficient. The mix is not that particular admixture is not in Life-365, so I need to go to lab tests and put those lab test results in the model. So that was C1556 for the apparent diffusion coefficient, which I got out of an ACI publication. Effects of silica fume, that directly goes in the model as an 8% replacement of the cement. And then I had to convert all of the ppm values to percent weight of concrete. But did this in a couple hours. It's a first estimate. If you want copies of the files I made and the smarter people in the room can do a more refined precision, I'm more than happy to send those to you. All right, so that's what I used from the inputs provided. And then these are the service life results that I get out of that. So for the control, it's around 20, 25 years. For the silica fume replacement, it's around 65, 75, 80 years. And then for HP40, 167, it's around 150 years. So big differences. So the best first outcome of Life-365 is that these guys don't overlap each other. if they overlapped each other, if one was 35, one was 36, and one was 37, you really don't know enough. There's not enough variation to be able to say anything about which one's better, other than they'll all last about the same amount of time. Where things get interesting is using Evan Bentz's approach for probabilities. One of the requirements of this comparison was see if you can tell, will the software tell you whether or not you get a 100-year life with a 90% confidence. And so that's what this graph does. This graph allows you to see, so the red one here is the control. This is the PDF. So you can see the mean, which is that dashed line, that's what ends up in the results, like 25. Here you're seeing some variation, here you're seeing asymmetry in that difference. But it's pretty tight. The variance is fairly short. So based on the lab results and the way the model runs, it's fairly tight. When you get into the substitute replacement, you're getting a bit wide. And then when you get to the HP, it's very wide. The PDF is very wide. So what I struggle with is how to use this information for good. Like, it's easy to use it for evil. Like, I don't know what it's saying. It seems like whatever my estimate is, it could be anything. It could be 10 years or 100 years. You have to be very careful interpreting that this is what this model is saying based on the laboratory results that it used to generate the model. That's all you can say for sure. You can't say that this is actually happening. The percent confidence, I had to practice this with the first row of the law, the practice it on a cumulative distribution function. 90% confidence. In the case of the base year, there is 90% confidence that the service life is 27 years. 10% confidence in that greater. Sounds a little confusing, but it's a probability curve. CDF. This is saying that at 90% confidence, the service life is 125 years, and 10% is greater. But 90% confidence will be 125 years. So the silicon fuel is pretty good in that. Now let's look at the HP. The HP is somewhere around 450 years. 90% confidence. You have 90% confidence. You have 10% more. The graph provides the data. The difficult part is probably what I think. It's doing it right now. It's using the information in the correct way. It's how you, and maybe you've got a better way to explain it. That was the best I could come up with, is a mathematically based definition of what the probabilities are. But what this is saying is that the control does not meet the 100-year requirement to 90% confidence, but the silica fume and the HP40 do for these mixes. Okay. Everything I've said so far is the first estimate. I may have fat-fingered in a value in the wrong place somewhere. I may have not thought correctly about what kind of structure this is and what the splash is. This is the first of probably 100 iterations on this that you do, where you just keep changing values and you look to see what effect it has, what effect the change in the depth of reinforcing. One of the cheapest ways to get service life is just increase the depth of the reinforcing. It buys you a lot, but maybe it's just not reasonable from a design or a delivery standpoint. But there's a lot that needs to be done in terms of just doing sensitivity analysis, which factors matter, which one can I forget that I don't need to worry about. I change this one 20, 30, 50%. It doesn't do anything to the service life. It changes it a little bit. I change this one factor and I get big, big changes. It speaks to the need for better lab results or new lab results that get you into that part of the service life prediction that's not being modeled well. Any questions about these results, the assumptions behind it, that part of it? Yes.
Thank you, Mark. On the cumulative initiation, my understanding was that it's supposed to be read the other way around. if you want 90% confidence, you should look for the 10% failure.
Okay. Okay. Now, I know the model works right. How I explained it may be wrong. In other words, I know how the software works. I'll tell you that. PDF. Straight on PDF. CDF is just the integration of this over time. So I know the graphs of it.
Yes.
The explanation of this.
I believe so.
Okay.
And that flips everything because instead of you mentioned the red line, 27 years, it's looking more like 12. And same happens. So basically it's whenever the red, the blue, and the green cross the 0.1 mark.
You're saying that it's the opposite.
Yes.
10%.
Because you want 10% of initiation, not so 90% of your cases should not have initiated corrosion at X number of years.
Can you do me a favor?
Sure.
Re-explain that graph.
So here's the failure. So it's whenever these lines are crossing there, that's the 90% level. Life-365 is very harsh when you put reliability. And so it's saying that even this super concrete is barely giving you 75 years, 90% confidence. This one sucks.
This one. So you're saying 10% chance to fail here.
Initiates the probability.
Yeah.
We're also not looking at the case of use and what this would point to is that we might do something better rebar. We got to get a load of water or something. Okay, gets it under your what?
Right there. So in 100 years, this one has 100% chance. This one has 80%. Corrosion. This one is 100%. Okay. That makes sense. Any other questions? Any other corrections?
Maybe just an additional comment.
Yep.
I thought Life-365, you have like 6 years later.
Right.
The application version, not right.
Right.
So you have the initiation rate, but
Right. Neil explained target for this session was to get 100 years of initiation time, 90% confidence rate. So you are kind of excluding initiation time.
right. But I don't want people to be thinking I'm sure all going to be 10% delaminated.
Any other corrections?
So it should point out that the 750 parts per million, normally 500 parts per million or 0.05%.
Right.
But that was based for. So we do the probabilistic technique.
Yeah.
So we can do the half is going to cover 500. All right, so that's part of the reason. Good enough. It comes up to about 0.4%.
Okay.
This will be correct. Why would we take a cement content?
Yeah.
But that, that comes.
Yeah.
Notwithstanding the left.
I did not, just to try to keep it simple. And
that would have shown that why do people put stainless steel in it?
yeah.
That 35 requirement. Because of this, like using those.
Yeah.
No variety to do all the time. You can do it all the time, you have a concrete that won't come out of blood. The finisher. So you can pay an hourly back by your hand. And it what concrete mix you use here or any of the models, they'll tell you that how long it lasts, but it doesn't make the lifetime that you have, not any inhibitor, whatever, membrane, whatever you want to do.
Right. So in closing, so the road ahead for this model is a consensus committee-based model. That's both good and bad. The good is that as a group, if there are new tests and there are new results and new admixtures like this HP, and the other one starts with an M I still can't pronounce. Once those are in the standard, implementing those in the model is straightforward. But the model is trying to be very careful about not just sort of courting vendors and suppliers that have the next great thing, that if you just stuck it in the model as a drop-down, then everyone could have the benefits of recyclable steel or something, whatever. Really important that we stick with the subcommittee A, which is based off of committee, new test procedures, and new process. There are opportunities, lots of opportunities with the software to come up with new geometries for the concrete, new exposure conditions, that kind of thing, without in any way altering the basic mechanism of how the model works. And then finally, if there's any information you want about it, Jim Wolfsfer or myself are happy to answer questions or send these project files or talk offline. Yes?
Can I ask another question? Can you go to the table where you had the concrete assumptions forward? That one? Yes. So, can you clarify, did you use the diffusion results from Neil, or on the blank lines on control in SF8? So
we use what was provided by Life-365.
But Neil, you have results for that, right? You showed diffusion?
Right. So what I tried to do in the interest of comparison was if I could use a Life-365 setting, I did. If I couldn't, then I would use one of the values that came out of the results.
Okay,
but I
so
tried
then there's different...
Yeah.
It's not going to be great.
Okay, thank you. Another question. How did you account for Life-365 having a build-up period, but FIB not?
Say it again?
No, the build-up period for the chlorides.
Oh.
So like
right.
Those kinds of parameters that are in one model, but not the other one.
Yeah. So I don't want to make this sound like a blanket statement, but maybe it is. It's not hard at all to just go back into the model, change that exposure to immediate, and see what effect it has. It's likely going to change surface life.
You went then the more conservative side?
I just went for whatever. So the idea in terms of comparing Life-365 with others was to just try to use as much of what it offers already as possible, just as a means of comparison. A bridge engineer may come in with very specific ideas about what should be used for roadways, for example. My point is simply that you can go back in and change that one. You're probably going to get a year of additional time-initiated corrosion if you're delaying the buildup period. Mm-hmm. And you know why that is then, because the buildup is slower than immediate. In other words, you gain insight from how the model works by making these sensitivity analysis changes. Accuracy, in my opinion, is fleeting, given that there is so much difference in terms of how concrete is made, the placement, the actual exposure conditions, whether there's cracking or not. You're just coming up with the best estimate you can to compare across techniques. To try to hit that number exactly, I'm a little confused myself on whether these models are used appropriately to do that kind of thing. That's all. So whether it's 7 years or 3 years or immediate is not as important as understanding what these mechanisms are and what you buy by the particular exposure conditions, the concrete you use, how it's placed, that kind of thing, that insight. And then if you come back and you come up with a very detailed version of the model, my argument would be that it changes by maybe 1% in one direction based on a more precise set of parameters.
And last question, maybe more for Neil. Did the models use consistent coefficients of variation for these properties?
Yeah,
Okay.
so I use those coefficients that were given.
That were given by Neil.
Yep.
Okay, thank you.
Right, exactly.
Any more questions for Mark? Yeah, I think it's a relatively easy one. You spoke to varying element size and how that can change results by kind of the one-sided solution.
Yep.
About 12 years ago, I was reviewing a parameterized study using Life-365, and I zeroed in on the importance of discretization, and at that time, the discretization was fixed. So again, same cover, different element size, and kind of where that near-surface discretization landed relative to bar depth. And I don't remember if I was talking to Evan or whoever the programmer was at the time, but it was like 10 or 15 fixed discretizations regardless of element thickness. My basic question is that still, and it's not to denigrate the software at all, it's just recognizing the tool you're holding in your hand.
Yeah,
Is that
exactly.
still the case?
I believe that's the case now to try to account for that effect that we have. In fact, the manual now says like we're modeling chloride only down to the first 10 inches in that kind of slab.
Okay.
Because of that problem.
Yeah, is there any, I guess the question is there any, is discretization an input you can control, or is it a fixed value?
So Evan Bentz's original code was dynamic. It would change the discretization based on what those depths were.
Okay.
You can do that. It just means you need to document it, verify that it's working correctly, and then when things do change, that the model's behaving the way you designed it would and would code. It's dynamic based on those differences. So it's a more complex discretization.
Finance issue, and when you look at the computation power was different than what it is now. So if you run the model, you get results pretty much right away. So because it's a coarse mesh, if you start slicing it more finely, because it's longer, you can run models that are days. You get depends on.
So just understanding, I guess, that when we talk about parameters for this or any tool that we're holding in our hand, understand you may have variation due to coarse discretization that dominates over 10% differences in other, finely tuned input parameters. So it's just
exactly. Even the numerical precision of the numbers that are held in memory by, in this case, in the Java compiler, cause variations if you're not careful about where you're using that numerical precision. If you're dividing by small numbers, that kind of problem. You have to be very, very careful with it.
You got a very long time.
Yeah.
More important than your slab, you can look at. Slab isn't very thick compared to those. It's not one
Right. And going forward, obviously we're open to addressing those implementation questions that need to be done. So there's a basic approach on paper, then it's implemented in software. And there's room for expanding the implementation.
In the interest of time, we're going to move to the next speaker. Thank you very much.